I left Oregon State in 2007 at 58 years old and did a combination of consulting and growing garlic commercially with a friend of mine for the last 10 years, and I've got out of the garlic here recently. But I've stayed as a technical advisor to the California Onion and Garlic Commission, if you want to call it that, as they review grant proposals and award grants. So I've been hopefully up to date on what they're funding, and some of this is old news in a sense. Whoops, what did I do? There we go. Anyway, I'd like to share with you a little bit about the basic biology from a Western U.S. point of view of white rot, and talk about what I have worked on as a model for risk assessment of that disease, which is relevant in parts of the country or parts of the world, but it's still in development, so it's not a really finished model at this point. If you're not familiar with white rot disease, the upper plant is a garlic plant showing the typical white mold that you see at the base of the plant as it becomes infected. And if embedded in that are little tiny black sclerotia about the size of poppy seeds that are in the reproductive stage. It hits onions. Certainly worldwide, onion is more important than garlic, but I work a lot with garlic, so a lot of my pictures are of garlic. And you can see a mass of sclerotia, the poppy seed sized sclerotia that have formed on the base of this onion bulb. If the visibility was better, you would see embedded in the roots additional sclerotia that have formed in the root system. Most typically in the field, in a lightly infested field, or maybe the first time a field has manifests the disease, you see small patches of loss during the season. It's a killing disease, so plants die. And these patches can actually elongate along planted row during the season, depending on when they first emerge. And I've seen patches as long as a meter or two, sometimes from a single sclerotial infection. This is a picture of onions showing the same nucleus of plants here. It's a little more obscure because there's a lot of onion leaf death from other reasons in this field, but it's still showing the same locus of infection. This is a seed onion field in Central Oregon where I spent much of my career at a branch research center. And this is all death from white rot, these bare patches in the field. If you walk through the field, you see a lot of individual strikes that aren't as apparent from this aerial view. But this is a second or third stage infection from 1 or 2 crops ago. All these patches here started out as single sclerosum strikes, and the sclerotia were spread out in the intervening years between rotations. This was probably following a garlic field. This is a field from long ago. It's not a very good picture because it's aged. I took this in 1975, the first year I was a graduate student. In this field, in March, which is early spring, in the Salinas Valley where this picture was taken in garlic, soon after emergence, the field became 100% dead from white rot. In the previous planting, 10 years earlier, these side patches here were not part of that original field, but they were incorporated in the field, and with land planes and other tillage systems, sclerotia had moved out to these wing areas also, and those died within a few weeks. They were just a bit delayed by lower inoculum levels. So it's a pretty serious disease, and in the Western US, people tend to run away from it rather than try to stand up and fight, because the tools we have to fight it aren't that good. I need to keep drinking water or I'll start losing my voice here. So when I started working with the crop and the disease in the mid-70s, most people thought white rot pretty much acted just at the stem plate or plant level. They didn't really know as much of a root disease. But it is. It's primarily a root disease. And anywhere in the soil profile, in probably the upper 30 centimeters, a sclerotium can infect a root and grow up and kill the plant that root grew from. And in the process, it can cross over into neighboring roots of the same plant and neighboring plants. And that's how you get these loci of infection in the field as it mows them down, up and down that planted bed. If you get a high population, you don't see that local infection. You see just mass death from massive infection of many roots on all the plants. And that's fairly common also. It doesn't have to be root contact. The fungus does not grow well in soil on its own, but growing from an infected allium root, it can grow out into the soil 2 or 3 centimeters, maybe longer, further, and infect a root that far away. And so it's a very powerful fungus in this respect. This picture may show a little bit better that it can form sclerotia in those roots as it makes that passage up towards the bulb. But most of the sclerotia are produced on the rotting bulbs themselves. Early on, we had no idea how much fungus caused how much disease, or really where it was coming from in the soil. And so we created these small test plots that were individually infested at various levels. This is back in the mid-70s. This is quite old picture. And taught ourselves what its capabilities were. The sclerotia were tilled in at different inoculum densities down to about 8 or 10 inches deep, which is 25, 30 centimeters, maybe 20 to 25 centimeters deep. And the deeper they were, the slower it took to come up to the surface, which makes sense because the fungus is rather slow growing all by itself. So it took time for the roots to get down to the fungus at some depth and time for it to grow back up. On higher infestation levels, there were more sclerotia near to the bulb of the plant, and so those tended to die earlier. And we developed a lot of seasonal progress disease curves. This is garlic that was planted in the fall and overwintered, and this is disease progress as symptoms showed up beginning in the spring, and this would have been end of February, early March at Davis, California. This was previously uninfested soil, so we went out on a limb and made these artificial infestations in an area that was not really an allium production area. And you can see these are very high infestation levels. We lost everything almost immediately. And these are almost unrealistically high. 1,900 sclerotia per liter of soil is incredibly high for this fungus. It wouldn't necessarily be high for a lot of fungi, but it is for this one. And then grading all the way down to some of those bed sections, we threw 1 or 2 sclerotia in. And we still got up to 10% loss from a single sclerotium or 2 in those bed sections, and up to 40% loss at the limit of our soil detectability, which is about 1 sclerotium per liter of soil, which is a little bit heroic in itself. So even if we can't find the fungus, we know fields can lose up to 40% of the plants in at least patches of that field. That's a pretty powerful disease. Oops. Okay. And this just shows you a set of curves at the end point at harvest. Most of these are garlic curves. Some of are onion for overwintered onions. And you can see at the detection level of our inoculum or assay, we can lose 30, 40, sometimes even 50% of the crop. So our soil assay really is not that good. And at higher than, say, 10 sclerotia per liter, we're pushing up to 80 to 100% loss. And we have fields or sections of fields that are infested at numbers much higher than that. So those are the fields that people walk away from when they happen. At very low levels, we can't detect it. We might still lose 10, 20% sometimes, which is a frightening proposition in its own right. This is a field in Central Oregon that had 2 previous allium crops, one an onion seed crop in the late 60s, and another one in the garlic crop in the 70s, and this was planted in the early 90s. And the previous incidences have been either not known or ignored. And this field eventually went down at 100%. Early in mid-spring, you can see along this front edge, all this off-color garlic are those individual loci of plants that are dying. And this is a patch that's much more highly infested. There's another one back here. But these eventually all coalesced because they were everywhere, and the field went down quite hard. This was a big shock to our local growers because we'd had no losses at this level in Central Oregon up to that time. So if I refer back to that yield loss curve, inoculant density yield loss curve, we know from lots of experience that we can't control the fungus with standard fungicides at levels that are very high. We don't even try. At lower levels, we do okay, but our ability depends on the inoculant levels. This is a slightly higher inoculant level than this. This was uniformly infested in a farmer's field that had very low background level, but with white rot being a zero tolerance disease on garlic seed, he was never going to plant this again anyway. He let us artificially infest this section of the field. This was infested at about 6 Sclerotia per liter soil. This one was about 3. And it was really night and day. Some of our fungicides did quite well at this level and did not do as well at this level. So that's kind of preliminary to this risk modeling that I want to talk about. I failed to mention earlier, but the pathogen, Sclerotium salpivarum, is a sterile fungus. It's an ascomycete related to Sclerotinia, botrytis, but it biologically is much more narrow in its appearance and variability. It's not very variable, and people don't find a lot of variability around the world. It's a cool weather fungus. It can germinate in 9 to 22 C with an optimum of 15 to 18 centigrade. But functionally, it's a little more restricted than this. At the higher end, it seems like it's not very competitive at its upper end. It gets eaten by other things as it near its upper temperature limit. And below about 10, it's just so slow that we kind of ignore that in terms of modeling its activity in the field. The fungal growth, the hyphal growth itself is a little bit wider range, but again, it seems to have this upper limit at about 21 centigrade and just fails to compete with anything in the soil, even though an auger and sterile auger grow a little bit hotter than that. So all the modeling that I'm talking about, the effective temperature range that we're looking at is from about 10 to 21 centigrade. This shows a map of the US and Mexico and where onions and garlic are grown. The big areas are California, parts of Oregon and Idaho, parts of Oregon and Washington. And there's a fairly big area in Texas and some smaller ones in New York and Colorado, New Mexico, up in British Columbia and in Ontario, Canada, and a few other places. But the big growers are in the blue marked areas. Worldwide, it's everywhere. It's even down in the tropics as long as you go into the highlands or into the mountains. I've been in fields in Guatemala at 2,500, 3,000 meters, and it's a dynamite disease in those areas. You get down in the lowlands, it doesn't exist. It's too hot for it. These are the Sclerotia. They're, like I say, about poppy seed sized. And this one in the center is germinating. And it erupts, blows out, kind of like Sclerotinia does, in a plug. And otherwise, it's thought to lie dormant in the soil for a very long period of time. The disease basically has not been controlled by either crop rotation or plant breeding. There's no sources of resistance in alliums that anybody's detected. And these Sclerotia are thought to live up to 40 years, although that's questionable. They do last a long time, too long for most people to wait. When they germinate, and most of the work on the fungus was done back in the 60s and 70s on the very responsive germination it has being stimulated by the onion and flavor compounds in garlic. They're 3-carbon sulfur compounds like allyl and propyl sulfides. And they're the same things you taste and smell when you eat a garlic or an onion. turn this fungus on, and it will germinate. And it will germinate en masse. Essentially, every sclerotium in the field will germinate, which is kind of its Achilles heel. And as mentioned in the introduction, we've tried to take advantage of that massive response by applying stimulants in the off-season. And it actually works quite well, but commercializing it and systematizing it's been very difficult. People have been working on this for 25 or 30 years, and we're not quite there yet. This is a fungus germinating and infecting. You see some infection cushions on that root. So as I get into my concept of the model and how we might better understand what's happening in the field, if a seedling is infected, who misses one plant, and it's not even noticed most of the time. And there's not a lot of roots there to turn this fungus on to grow. So really the disease gets going when there are more roots to elicit more stimulants to cause more infection. And so the model I'm working on, the disease starts when you have enough roots to leak out stimulants and enough roots for the fungus to find and begin to grow and cross over on root systems. And just arbitrarily, I've chosen a 4-root point in the season. If you started at day 1 at planting, it's too early, the fungus is not active. And if it just has 1 root, the fungus hasn't got anywhere to go. And so I wait to start the model progress until there's enough roots for disease to progress. I showed you the picture earlier where it's growing up and sideways along the row, and it grows, it's a slow-growing fungus. I'll show you how slow in a little bit. And it grows up and out. And once it grows fastest in the area with the highest root density, which is up near the base of the plant, in the top, 3 or 4 centimeters below the plant. If all my plants look like garlic, that's because they really are. I apologize. We tend to plant garlic a little deeper. There are some soil temperature implications on that compared to seeded onions, but basically the model is similar. And as I said, if it runs into temperature above 21.1 C, which is a little more detailed than I really know it to be, let's say 21, it stops and it dies. It has to be growing on an onion root or the bulb. And if it hits this temperature, these roots die and they no longer support the growth. It's not saprophytic, it's not competitive on anything else. So basically it goes away. And so there are limitations depending on your onion or garlic growing season on whether the fungus can be successful or not. If it's already penetrated into that root zone and has not quite reached the stem plate, it'll die in this zone. And so that's to our advantage. So this is old data and it needs to be improved, but basically based on work that I did a long time ago as a graduate student, I determined, at least for garlic, that it takes time for the plant to grow down to where the inoculum is, takes time for it to infect, takes time for it to grow up. And so you have these time lag delays before you see symptoms manifest at the stem plate level. And so for sclerotia that are at the 5 centimeter level, it takes about 35 days after a 4-root population in that area for infection to occur at the bulb. And as you get progressively lower, I hope you can read this data, it takes longer for that whole process to occur. And so part of the model takes advantage of those time lags. That's just the same picture I showed before. Oops, am I going backwards? Okay. And so what I've done is gone into regions that have good soil temperature data. You can either use data loggers in individual fields, or you can use these regional weather stations, which we have all over the western US to enhance irrigation management, evapotranspiration data. And if the stations are on irrigated ground and have an irrigated crop underneath them, we can use that data as to simulate what's going on in an onion or garlic field and get close enough for the model purposes. We can't use data loggers or in dryland soil. And we found that management of the station is critical. There are a lot of stations in irrigated fields that are useless to us because they just aren't managed very well. And so some of the data I'll show you is from some very well-managed ones. And I could show you lots of other ones, but I wouldn't use that data because it's just not representative of good irrigated crop conditions. I'm going to first talk about southern Texas, which is kind of out of my range of expertise, but they grow an overwintered onion there, and white rot tends to like cooler weather, so one worries about whether Texas can get white rot. It's never been reported there, and it is a hot area, but still it's a question mark. I got involved in that because I was working with some people in Mexico that were working on applying stimulants, and I found out after the fact they'd been sending soil to a lab up here in southern Texas in the middle of the onion growing area, and the guy was tossing the soil out the door when he was done with it, and I freaked out. You can imagine thinking that he was going to crap up 15,000 acres of onions in southern Texas. And so I had him immediately send me a whole bunch of soil data, and this was a long time ago. And I backed off being quite concerned, but it was fairly irresponsible for them to do that. When you look at the southern Texas soil data, they plant their onions back in mid-October, maybe into November. And by the time the temperatures drop below 21 centigrade, they have more than 4 roots. So the plant is available if the fungus is there and it could respond. And this is just a typical overwintered onion from 2012, 2013, a year. And so you can see that beginning in about towards the end of December, the soil temperature dropped into the conducive range for white rot to be active. And it stayed there for about 33 days before it eventually warmed back up above 21 degrees in late January. And basically, if you recall that data I showed on the time response in the fungus growing down, the roots growing down, the fungus growing back up, it takes longer than that. So this year, they would never have seen white rot, even if that field had been highly infested. It just wouldn't have occurred. Maybe at a high infestation level, they might have seen a little bit from very shallow infections, but the shallow infections tend to get tied up with dry soil too, so we tend to ignore the stuff that's right at the soil surface. And it turns out that this is really typical. This is a typical year, or actually even a long window of opportunity compared to most years. So out of about 20 years, I found 1 year that had a long enough gap in there for white rot to take advantage of it. So I stopped worrying about southern Texas. But that was kind of an early impetus to me to look at this a little bit deeper. The next one came in eastern Idaho, which is, again, one of the really big onion areas of the country. About 20,000 plus acres of onions are grown there and overwintered. I'm sorry, it's not an overwintered onion, but it's an area that has a cold winter and a hot summer. And so you have spring and fall that are conducive to white rot. And they've never seen white rot on their main crop, which is planted in May or April and harvested in October, roughly. But they do grow some seed onions in that region. They have about 1,000 acres of seed onions. And I was called to get involved in a case of a seed onion field that went down about 100% in the very late 1980s. And it freaked out the local industry. They'd never seen white rot in the area, and here they have a field that is 100% lost. And it turns out that this onion seed field had probably had white rot 2 or 3 or 4 times before, and nobody told anybody. The guy was actually in the process of disking under to hide the fact that this had happened when he got caught by his neighbors, and the stuff hit the fan, so to speak, and every regulatory body in the area got involved, and the field was quarantined. And I was the only one allowed into the field for a couple of years because we talked them into letting us do some stimulant research on control of white rot. And I told them, I said, you overreacted. You shouldn't have quarantined this field. What you should have done is gone and plant your main crop of onions, and it would have snuffed out the fungus to a great extent. Well, they weren't going to believe me. They were too neurotic about that. But they did let me test allyl disulfide to control white rot in the field. And at the same time, I planted some onions to prove to them that they would not get sick. And I'll show you a picture of some of that later. And I based that on, again, another temperature analysis of the area, plus their long history of not getting white rot in their main crop. And so what happens this is a cold area. In the middle of winter, it's actually below freezing, and the soils may freeze themselves. In the middle of summer, the soils can get up to close to 25 centigrade. And so they pass through this window between 10 centigrade and 21, where the fungus can begin to grow. And if they plant here in mid-April, the fungus could begin to grow and infect and move up the root system. And in this year, they had a 39-day window. And if that earlier set of data I showed you, 39 is just on the edge of the possibility of white rot showing up as a symptom disease. But it crossed the line, and the fungus would have died out before it really manifests. And then it goes through this hot period in the middle of summer where the white rot fungus can't grow. And then it starts dropping back down again this is the mid to end of August. And then they might not harvest till mid-October when it has this nice little window when it could be active again. But realize that during this period, if there were Sclerotia in this field, they would have all germinated. And there's really nothing left here to take advantage of the late season part of this curve. That would not have been true if, so let's say at the soil depths of 20 centimeters, which is the gray line, if that had never crossed the 21 line, you would have had the fungus active deeper in the soil, and it would have been available to move up at any time that the shallower layers were cooling down. But that didn't happen. Even at 20 centimeter depth here, the curves are at 5, 10 centimeters. I didn't make that clear, sorry. And that's typical. This is a typical curve for this area. I've looked at 10 or 15 years worth and never seen a year where this wouldn't have happened, basically, in this eastern Idaho area. And so, that didn't convince them totally. This is just another year showing the same data. Again, it had this window of opportunity, but it runs into this hot temperature zone, and then it just, there's nothing left to recur in the fall. Now, this is some old DADS data from the early 90s that we did. And the thing I really want to show you, two things, I guess, is that DADS worked. We got rid of most of the sclerotia by applying. These are based on inoculum densities transformed into percentages of plot by plot, which is kind of ugly data, but it looks good when you transform it to 100%. And over time, there's gradually white rot slowly dies off, but it never gets to the point where you would ever replant into it. This is still way too high to live with. But at increasing levels of DADS applications, we were getting rid of 98, 99% of the sclerotia with those applications in the soil. But onions did the same thing. Over the 90-91 season, just growing onions knocked that population down too. We planted onions in these plots, and in the spring, we overwintered them. We harvested half of them in the fall with 0 white rot. We left the other half to overwinter, and during the spring, we lost 100% of them. So it's very temperature dependent. In this area, you wouldn't want to grow an overwintered allium. You're home free planting a spring planted allium that you fall harvest. But they still have a hard time accepting that. This field remained quarantined for the next 25 years. Finally, the farmer was about to sue the state because they couldn't really justify this, and everybody finally talked a developer into putting a big industrial complex on top of this whole ground, and the problem just kind of went away, theoretically, even though he would have moved sclerotia everywhere in the process. Anyway, this just shows the same data, but with emphasizing the winter. And so if you plant your fall planted onions, let's say a seed onion back here in July, this would be here. These are seed to seed onions. So you plant the seed, they establish in the hot part of the summer, then they go through this fall where white rot can jump on them, and then it goes dormant. So the fungus just goes dormant along with the plant. And so you kind of cancel this out as far as the activity period goes. So you have a spring activity period that you just add on to, a fall activity period that you just add on to a spring activity period, and you get well over 100 days of white rot activity, and those plants are going to die. And so that's what you don't want to do in that area. This is just another year with the same pattern. So these were kind of got me a little bit further along the way to developing this model in these really clear-cut areas. But onions are grown in more borderline temperature areas all the time. The same area that represents Idaho represents central Washington too. You don't get white rot on spring planted onions in central Washington. And there's 25 or 30,000 acres of onions up in this area. California's more complicated. It has a lot of garlic, has a lot of dehy onions that are planted in the fall at various points of the fall or even into the winter. So you got all these temperature variations on the theme. And unfortunately, I don't have as good a temperature data in California because their weather systems aren't assembled so that you can get temperature at different strata of the soil. But sometimes you can get some from a researcher that happens to have some data loggers in a given field. But, so looking at Central California, down west of Fresno, say, this is a couple of years of data, but only at 15 degrees, I'm only at 15 centimeters. So I'm lacking the data from, say, 5 and 10 centimeters or something in between, like 7.5 would be useful. So I don't have in midsummer, I don't have the limiting temperatures up near the stem plate of either onions and garlic to quite know in terms of the model where the season would start and shut off. Based on 15 centimeter data, the seasons are pretty long. If you plant dehy onions, say, or any kind of onions in the fall, you get a period of winter activity and then a period of spring activity, and that can add up, we think, to, in terms of the model, plenty of white rot, and they in fact do get white rot on those onions. And so I just can't justify the model as well in terms of their fields. For garlic, the same story. Garlic goes down hard in California, being overwintered, and again, it's fall planted, spring harvested, and you get this fall-spring period of activity. But again, the model isn't quite as well developed for those areas. Where I have more interesting data with respect to, say, Tasmania is out of Ontario, or north of Ontario, Canada, working with a pathologist up there, Mary Ruth McDonald, who's a good vegetable pathologist. She's provided me temperature data for their spring planted onions, and it's a season where they know in a cold year they get a lot of summer white rot. In a hot year they don't get very much, and so the model might be more useful in that area. And I'll show midsummer when it usually crosses a 21-degree centigrade line. Not always, though, and not always at every soil depth, like it did in Texas or Idaho. And this year, the lines were pretty close to each other, and so it stopped. According to the model, it would have stopped right here in the first week of July and stayed inactive through till early to mid-August. And this gap in here, I'll show you the data here in a second, how long that is kind of is critical. And then whether it can be active in the fall. It's the same story as it was in Idaho, but a little closer to the tolerance levels of the fungus. So looking at their data, this is kind of hard to see, but so they planted in I got that wrong here. Anyway, they had 4 roots by mid-June, but the disease of the fungus would have stopped activity at all soil depths around the 1st of July. And so this is the number of days it spent in a potentially active stage, which is far less than it needs to cause symptoms. So there's a gap when it's too hot, and it can restart growth early August. And depending on when they harvest, there's a period of time that it might be active. And again, for an early harvest, it's a very short window. They wouldn't see very little white rot or none. For a middle time period harvest, they're still below that period, which is a minimum of 35 days or so at the shallow soil depths. And for a late harvest, they do cross that line, and they potentially could get white rot late in the season from shallow infections. And looking at their old data, it was a year when they had relatively little white rot in their field trials. And it kind of fit the model. We thought it looked pretty good. And that's just to remind us of these time delays at the different depths. So looking at another year where they planted and would get 4 roots available here in May, at a fairly short window before it got too hot, but it didn't get hot enough at the 20 centimeter level. So there's no reason that white rot couldn't have stayed active down in the soil lower than, let's say, 15 to 20 centimeters. The temperature did blip above 21 briefly, and so that's questionable whether the model is robust enough to call that a point where it would have shut down totally, or whether it could have bridged that gap and maybe survived. And you don't have temperature at every depth, and so there's potentially some white rot that could have carried through that season at the lower depths and then risen up as it got into the fall period. And in fact, they did see a fair amount of white rot late when they did in their late harvest. And it would have been contributed from all 3 levels in this case, including the deep levels. And again, it kind of fit the model. We thought it looked pretty good. And one final, I don't know if I have 1 or 2 more years to show you, but this year they planted earlier. It was warmed up early, so they planted, and had a fairly long period in here before it got hot, much longer than the previous years that I showed you. But it did shut off here in the middle of summer at all this levels according to the model, and then they had a period in the fall at least, but it got hot again here later in the fall, so the fall probably didn't contribute much, but we worried about what they might have seen from the first half of the season. And so the model said that they would have had white rot loss from the first half of the season. They would have had a little bit added onto it later in the season. And in fact, it was a bad white rot year for them. They had a lot of white rot. And again, it kind of fit the model. Even though we think the model can be improved, it seemed like it has some promise. And looking at a lot of years, it looked like if the model tells us it was going to have a very low white rot for 2 years, and if they actually experienced very low white rot for 2 years in a row, then the 3rd year was actually pretty low, even if conditions were right for intensive white rot. And what we rationalized is that with 2 years of stimulating the Sclerotia but failing to reproduce, the population had dropped. And by the 3rd year, they got relatively little white rot because the populations were very low. We don't have sclerotial numbers to back that up with, but it does match our other research. Unfortunately, even 1 season from a very low incidence is enough to build those numbers back up. And so, the 4th year, you have populations right back at you again, And so even 1 year of very low white rot, the fungus will over-reproduce on those few plants that die. And the last thing I'm going to talk to you about is a conundrum that I lived with for many, many years. When I was as a grad student and years after that, we used to have Egyptians come by and talk to us about how they might control white rot in Egypt. And they only got it on their midwinter onion crop. And it was their export crop that was probably competitive with your onions in Europe. And it was the most valuable crop that they grew. They didn't see it the rest of the year because it's just too hot, and they knew that. But in the midwinter, they thought, how can we control it? We'd never had too many good answers for them. But I used to ask them, well, how about garlic? It must be just as bad. And they said, no, garlic doesn't get white rot in Egypt. And that was the conundrum. How can that be? And I lived with that for about 30 years until I finally went to Egypt one time in the middle of winter. They asked me to come and talk to them about white rot there. And I saw what they were doing. And it finally made sense. Most of their onion crops were seeded or transplanted fairly shallow in the soil, but that winter crop, they were putting those transplanted onions down about 7.5 centimeters, where the soil was cooler. It was winter for one thing, so even in a hot area, that soil was probably cool enough for rot to occur. They were laying the garlic right on the surface. They weren't even bearing it at all. And so the temperatures up here are hot. And so the garlic just wasn't getting any white rot. Well, so I solved my own little problem after about 30 years of wondering why that could be.